Hello everyone, Dr. Chen here. So let's study Newton's third law in this video. Newton's third law says, to every action there is always an equal and opposite reaction, or the forces of two bodies on each other are always equal and are directed in opposite directions. To put it in very simple language, now we have two objects. Object A has a force Fa on B on object B, then there has to be a force from B on A, and these two forces Fa on B and Fb on A has to be equal magnitude and opposite direction. This is Newton's third law, and we call those two forces action-reaction pair. Now here we want to emphasize, if we recall what is Newton's first law and Newton's second law. Newton's first law, Newton's second law, they are all only about one single object. But Newton's third law is about two objects. Object A and object B. The force from A to B and the force from B to A, they have to be equal magnitude and opposite direction. This is Newton's third law. They can be verified in NAB that we have two force sensors and we can have them apply force on each other through a rubber band or directly bumping into each other, and we can measure the magnitude of the force on those two sensors. They always equal magnitude and opposite direction, no matter how we change the force between them. Now, after we read the statement, let's try to answer this question. We have a very tiny toy car, like this small, had head-on collision with a truck. Now the force from the toy car to the truck and the force from the truck to the toy, which one is larger, if there is any? What is Newton's third law? Let's recall what is Newton's third law. We have object A, object B. The force on them has to be equal magnitude, opposite direction. So this is the force from the truck and the toy car, and then this is the force from the toy car and the truck. These two forces form action-reaction pair, so they have to follow Newton's third law, equal magnitude, opposite direction. So there's a correct answer. C. The toy car exerts the same force on the truck as the truck exerts on the toy car. And we have Newton's third law phenomenon in everywhere. For example, baseball game. When the catcher catches a baseball, there's a force from baseball on the hand, and then there is a force from hand on baseball. Same for train collide with bus, Earth, and satellite. Let's see how the force works out. So there is a force from baseball on hand, then there is a force from hand on baseball. This one, we have a force from train on the bus, we have a force from bus on train. Okay, the Earth has a gravitational pull on the satellite. Now Newton's third law now this time tells us the satellite also has a force on the Earth, pulling the Earth towards the direction of the satellite. We'll come back to that in detail when we discuss gravitational force. And this one actually have effects. So we usually see the moon is orbiting around the Earth, but that's not actually the true story. The true story is that the Earth and the moon, they are both orbiting around the center of mass of the Earth and the moon system. This is the actual scale. This is what action. So the Earth is orbiting around this point. Earth is orbiting around this point. Moon is also orbiting around this point. So not only the Earth has a force on the Moon has a force on the Earth as well. Okay, try to answer this question. We have a boat pulling a surfer. We have four forces. The force of the boat pulling the rope, the force of skier pulling on the rope, the force of the boat pushing the water, the force of the water pushing the boat. Which two forces are action-reaction pair? Now, what's the requirement for action-reaction pair? It has to be between object A and object B. So those two forces can only involve two objects. So let's see 1 and 2. Boat pulling rope, skier pulling rope. The force 1, boat, rope. Force 2, skier, rope. So you have three objects. So 1 and 2 is not action-reaction pair. 3 and 4, boat push water, water push boat. A push B, B push A. Is it action-reaction pair? Yes, right? So B is the correct answer. Now let's add C. Boat pulling rope. 3. Boat pushing water. Well, not at all. There's no common object. Oh yeah, we have common object. So it's boat, rope, boat, water. You have three objects, so no. 2 and 3. Skier, rope, boat, water. Yeah, you have four objects. Definitely no. Look at this example. So we have a double punch. Mayweather punched Pacquiao on the face and Pacquiao punched Mayweather on the face. Is those two forces action-reaction pair? So the force from this punch to this face and the force from this punch to this face as action-reaction pair? Then says no. Now for this punch, the reaction is from the face to the face. For this punch, the reaction is also from the face to the face. And then we apply Newton's third law to run, to jump. So try to take a walk. Try to take a walk. And try to notice what's the direction you apply your foot on the floor. What's the force you apply to the floor? Is your force forward or backward? And you would observe the force you apply to the floor if you want to walk is actually backward. So you push the ground backward, and the ground is going to push you forward. Like this athlete, this dolphin athlete, she pushes the ground. She pushed the ground with the force like this, and the ground pushed her in this direction. So she can move forward. Now if we want to jump, try to do a jump and then notice what's the first action you did. You crouch down, right? You bend your knee a little bit and then you apply force downward. You apply force pointing down on the floor and then the floor gives you a force pointing up. So if this force from the floor on you is larger than your body, you jumped up. Just like what Gilmore did, who led the Dolphins to NCAA final in 1970. Okay, the next example we have in this lecture video, we have Superman and Supermoving have a tug of war. And let's see, no one is winning. No one is winning, so there are no, both of them are moving. So what would be the friction here? and a friction here. How is those two friction force compare? Well, the one is winning, so Superman is at rest. If Superman is at rest, the net force on Superman is 0. So this tension equals this friction. No one is moving, so Superwoman is also at rest, net force 0. So this tension also equals to this friction. And now we do know those two tensions are the same. This one equals this one. This one equals this one. So we can kind of reach a conclusion those two friction force equal.